All right, welcome back. Hopefully you all had a good summer break. On to lecture 21 now, More Exponential Functions. Exam 2 is coming up soon. It is July 9th to the 10th. It opens up on midnight of the 9th, ends at 11:59 p.m. on the 10th. So with that, let's move on to some exponential functions. And look at that, coronavirus. You can never escape it. This example was made in the spring, so we're not going to say currently because it is way past 60 cases. We're just going to say assume because we have a lot more than 60 currently, but that's okay. Assume there are about 60 people infected with the COVID-19 virus in the United States. Without precautionary measures, an infected person will spread the disease between 2 and 3 others during the contagious phase. And this will happen in approximately 1 month. Construct an exponential function to model the number of infected people over time. Okay, well, T, that's number of months. And C of T is going to be our exponential function. So it's going to be of the form A times B raised to the T. Yeah. Well, we're starting out with 60 infected people, right? So that A value is going to be 60. And it's spreading at a rate of between 2 and 3 people, right? So that's, well, let's take the average between the two. 2 plus 3 is 5, divide by 2, we get 2.5. So on average, it's increasing at a rate of 2.5 people, and then we raise that to the T, okay? So even if we just use this approximate model, right, what we get is a graph that looks like this. So after 10 months, we have 500,000 and change cases. A year, 3.5 million. And after 16 months, 140 million. And that was just off of assuming we have 60 infected people and they spread the disease to around 2 to 3 people. So disease modeling is quite useful. Now, getting back, I feel like there's a word missing there, but that's all right. Another example for exponential functions and their use is like investments and stuff and dealing with money. So if a bank gives you 50% annual interest rate on your $1 savings account with 2 options, which option will earn you more money? Well, the first option is calculate the full interest at the end of the year. Well, that's just going to be you're going to have $1 and you're going to get 50% more. So that's times 1.5. And that's going to give you $1.50, right? Second option is going to say, okay, calculate half the interest halfway through the year and the rest at the end of the year. So we're going to have that same $1 times, okay, if you half the interest, but half the year, we're going to get 1.25. And then we do that again, the rest at the end of the year, we're going to get 1.25 again. And that rounded off to the nearest cent gets you 1.56, $1.56. Okay. These are some common examples to use when talking about exponential functions. So let's talk about compounding interest. Compounding refers to the frequency at which growth is calculated. So you can compound yearly, 2 times a year, 4 times a year, monthly, right? That'll give you 12 times a year. So suppose we have an initial quantity P and it has a stated growth rate of R and is compounded n times per unit of time T. And the function that describes its growth is the following. We're going to have our initial amount P out in front and times 1 plus R over n raised to n times T. right? So it's the amount you start with, your rate per number of times you're compounding it, right? To the NT. So this is our formula here. So for this example here, if we want to construct a function for the growth of a $200 investment that has a 12% annual interest rate compounded quarterly, well, it gives us all the information we need. We just got to find out where everything plugs into. Well, first off, it says a $200 investment. So our initial amount, our p-value is $200. It then says at a rate of 12%. So R is going to be 0.12, right? Convert that percentage into decimal form. And then our R, that's R. The N is compounded quarterly. So annual interest compounded quarterly, that means N is equal to 4. So A of t, our function, is going to be 200 times 1 plus 0.12 over 4 raised to the 4t. Okay? So now we can answer a question like this. What will be its value after 10 years? Well, A of 10, right? T was representing the number of years. After 10 years, we're going to get, well, you plug in T equals 10 in for this, round off to the nearest cent, and that's a dollar sign. And we get 650 to 41. Okay. So the big thing is compounding interest. This is going to be our general formula to use for that instead of effective formula. Well, we'll get to that in a minute. All right, so what's actually happening here? So suppose you have a savings account that has $100 in it, and it grows at a yearly rate of 15.5%, compounded daily, okay? So let us express the value of the account after t years in the form of AB to the t, right? So, well, let's go back to this guy first. All right, let's look at this first. Well, the p-value is going to be 100. That's how much we started with. Our rate is 15.5% or 0.155. And then our n is going to be equal to, it's compounded daily, so that's 365. Okay. So now A of t is equal to, if we look at this formula first, 100 times 1 plus 0.155 over, I'm going to put a 0 in front of this just because my handwriting is terrible. 0.155 over 365 raised to the 365t. Now this we can rewrite as 100 times 1 plus 0.155 over 365 raised to the 365 and then raised to the t. So that we get, this is our A, this is our B, and that's to the t, right? So this approximately equals, if you round off, to 1.1676 to the t. So if you round this guy off, you roughly get that. And so by what percentage does the value actually grow over the course of 1 year? Well, that's when we look at A of 1, and we're going to use this formula. So it's going to be 100 times 1.1676 to the 1, not to the t, to the 1. That's going to give us $116.76. So it's asking for a percent. So how much of a percent increase is it from 100 to 116.176? And that is a 16.76% growth over the course of 1 year. Okay. So actual growth versus, well, we get into what's called nominal versus effective growth rates. And that's what we're going to talk about next. Nominal versus effective. When growth involves compounding, there is a difference between stated growth rate and then the actual amount of growth. So the stated growth rate is the nominal growth rate. Then the actual amount of growth is the effective growth rate. So looking back real quick, it's stated that we grew at 15.5% compounded daily, right? So that's the stated growth rate. And then how much does it actually grow over the course of 1 year? It grows by this much, right? Looking back to that example. So let's look at another one. A credit card company charges 29.99% annual interest on your debt and is compounded, sorry about that, and is compounded monthly. What is the effective interest rate you pay? Okay, well, let's find out what we have again. R is going to be 0.2999, right? That's our percentage. Our N is going to be, it's compounded monthly, so that's 12. And so what we really care about is A, B to the T. What we care about is this B value. That's going to give us the effective rate. So 1 plus R over N, so it's 0.2999 over 12 to the 12T, yeah? Well, when T is 1, right, that's going to give us, what does this boil down to? Well, number crunch, plug in 1 for T, and you get 1.345 roughly. And that is going to be your B value, which is going to be the effective rate. So your effective rate, R, is going to be 1.345. Subtract 1 off, and we get 0.345, which is 34.5%. Okay. So if it's asking for you for an effective rate, you want to find out what that B value is, right? If you start off with compounding, say monthly, daily, something, you convert it into an effective interest rate. Well, in this case, interest rate, but effective rate. All right. Well, is there a way to make the perfect investment? Well, consider this. You put $1 into a bank account with 100% interest rate for 1 year, and you are allowed to compound it as often as you like. Can you obtain unlimited funds by compounding often enough? Well, we're saying that P is going to be 1. We're saying that R is going to be 1. And that time T, we're doing this for a year, that's going to be 1. So for this guy, we're going to have 1 times 1 plus R over N to the N, right? Just plug in the values here for this guy. So at yearly, that's N is equal to 1. We're going to get $2, right? That shouldn't be an R, that should be a 1. Yeah, it's 1 plus 1 over N. Technically, I don't even have to have the 1 out front here, but I have it anyway. So semi-annually, N is equal to 2. If N is equal to 2 and we solve this out, or just evaluate it really, we get $2.25. Monthly, N is equal to 12. Plug in 12 here, plug in 12 there, figure that out, and we get that it's $2.61. Daily, N is equal to 365. the amount is, again, these are all rounded to the nearest cent because we're still working with dollars. $2.71. Hourly, N is going to be 365 times 24. 365 days times 24 hours in each day. We're going to get $2.72. Every second, N is going to be 365 days times 24 hours times 3600. That would be times 60 hours, then times, or not hours, times 60 minutes, times 60 seconds, but multiply those last two and you get this. Anyway, that's going to get you $2.72 again. So there are some limits to compounding. So if we look at the graph of what's just happening, like of this guy, what's going on here, of this guy, what we get is a graph that looks something like this. And what happens is it sort of levels off as you keep going further and further out on N. And, well, it goes to something kind of important. And that would be E, the natural base. So the limit of that graph is E, 2.7182 nonsense afterwards, right? It's a transcendental number like pi. For history note, it was discovered by Jacob Bernoulli around 1618, and it was called E in honor of the mathematician Leonhard Euler. So, right, any positive number can be used as the base of an exponential number, but there is one that is special. E, sorry, I keep hitting the mic, but E is that special number. So, now that we know of this special number, let's look at continuous compounding. So, continuous compounding means that we are compounding something at every possible moment. So if you look back at this slide, right, we did daily, hourly, every second. And so if we go past that every second, every half second, every quarter second, every possible moment, we get continuously compounding. And for that, we use E as its growth rate. So if a quantity has initial value P, a growth rate R, and is compounded continuously, then its growth rate is described by the function A of T is equal to P E to the RT, or PERT. That's, yeah. So E is your base for how fast you grow, and that's every single moment. So a colony of bacteria initially contains 1,000 specimens and grows with a continuous rate of 9% per day. How large will it be after 1 week? Well, what do we have? We're going to write it in this form because it says continuous rate of something. It's growing continuously. We're going to have A of T is equal to our starting amount, which is 1,000, times E to the 0.09 T. That's our function. Our rate R is 9%, so that's 0.09. And so we want to find out how large it will be after 1 week. T in this case is in terms of days. This is per day. So A of 7 is going to be 1,000 E to the 0.09 times 7, which approximately is 1878, rounding to the nearest bacteria. Okay. There's a lot you can do with continuous compounding. And another one is continuous decay. So, strontium-90 is one of the primary contaminants at the site of Chernobyl's nuclear disaster, which happened in 1986. It decays at a continuous rate of 2.4% per year. If an area was contaminated with, say, 1,000 grams to start with of strontium-90, at the time of the disaster, how much of it remains today? Well, again, what are we going to use? We're going to use PERT because it is decay at a continuous rate. So P is going to be 1,000. We are starting with 1,000 grams. Our R is going to be negative, right, because it's decaying. Okay, so it's going down at a rate of 0.024, right? So A of T is going to be 1,000 e to the negative 0.024 T. And we want to find out how much of it remains today. Well, 1986 is 34 years ago now. Yeah, 34 years ago. So A of 34 is equal to 1,000 e to the negative 0.024 times 34, which approximately equals out to 442.2 grams, right? And so if we take a look at this graph, you start off at, say, 1,000, and we are exponentially decreasing. So we're going to go all the way close to 0, right? But anyway, that's a rough graph of it. And this is our fun decay problem. And also don't forget to use units, because we started off with units. Doesn't really make sense to say, oh, there is 442.2 left. Of what and how much is it like relative? So it is important to include units. So there's a couple of different ways we can express rates. And so the ways that we know of are A, B to the T, right? That's our effective rate. Compounding rate, that is P times 1 plus R over N to the NT. That's compounding N times at some rate R. And then our continuous rate is P times E raised to the RT. Okay, so we have a few different ways. And you can go back and forth between them. Namely, sometimes you will go from continuous to effective or compounding to effective most of the time. So one last example, still in the same thread of expressing rates in multiple ways. The same type of exponential growth can be expressed in any or all different ways. So consider the example. A population of a small city is 300,000 people and grows with a continuous rate of 5.6% per year. Construct a function in the form AB to the T that models the size of the town after T years. Well, we want to get to here, but we have a continuous growth rate. So it's going to be PE to the RT is what we're going to start with. So A of T is going to be, well, we start off with 300,000. Continuous growth rate of E, okay, to 5.9%. So that's 0.059 times T. This is 300,000 times E to the 0.059 raised to the T. Yeah. Okay, keep writing this 300,000 again. This guy is approximately 1.061 about raised to the T. So from this guy, now we're in the form AB to the T. So from this, we're going to get an effective rate of, well, what's the effective rate? 1.061. Subtract the 1 off, and we get 0.061. Change that to a rate, and we get 6.1%. So the effective wait, I misread something. Construct a function in the form AB to the T that models the size of the town after T years. Right, so we did that, AB to the T, and the effective rate is 6.1%. So It actually didn't ask for that, but hey, we found it anyway. So yeah, expressing rates in multiple ways is very important. Continuously compounding functions are also important, and we'll be talking more about that in the next lecture as well. But as for this lecture, we are at the end.